Hey, what's up, guys? This is Chung here. So today, uh, let's take a look at another classic graph problem here, which is numbered 261. Graph a valid tree. So basically, you're given like a number of nodes and a list of edges, right? So the edges has like from, not from to, since it's undirected. So there's gonna be so this graph links no, 0 and 1, 0 and 2, 0, 3, and 1, 4. And you need to return a true or false to check if all these edges with this number of nodes can form a valid tree, right? So for example, this one. For example, here there's a like five nodes, right? So 0 and 1, right? So 1, 0 and 2, right? 0 and 3, and 1, 4, right? And as you can see here, so and this is a tree, right? But how about this one, right? See this one, same thing here. 0, 1, right? 0, 1, 1 and 2, 2 and 3, and 1 and 3, right? So, and then 1, 1, 4 here. So this is not a, a tree because we detect a cycle here, right? Or a circle, right? So a tree, right? So what does the tree means, right? So a tree, you cannot have a circle, right? If you have a circle, then it's not a tree, right? And so basically two conditions to form a valid tree from all these edges for this all the nodes. First one is you cannot have circle, and the second one is you have to link all the nodes, right? Let's say for example, if you have like 0, 1, and 2, right? 0, 1, and 2. And then there's like this 3 and 4, right? So this one is a tree. This one is also a tree, but it's not. But there are two components. There are two. It's like it's a forest, right? So basically two conditions. First one, you cannot have a circle in the in this subtree. Second is second one is all the nodes have to be in the same tree. So I'm gonna talk about three very common solutions. First one is gonna be the DFS traverse, right? Second one is gonna the BFS traverse, and third one is the union find. Okay. So mm, so for the first two, the DFS and the BFS, for both of them, we need to construct a graph based on this like edges. Basically, with those edges, we're gonna create like a graph with a key is the node, and the value is the neighbors of that node, right? So basically, once we have that graph constructed, we can just simply start uh, traversing that any node, right, in that graph, right? And in the end, let's say we can just start traversing, and once we traverse, we either use DFS or BFS, and in the end, once we traverse all the nodes by using that graph, then which in the end we check if we have seen all the nodes, right? Okay, cool. Let's start coding, right? Let's create a graph here first, right? And then default dict, right? And then it's gonna be a list. So uh, very like uh, standard way of creating a graph, right? For edge, right? In edges, right? Then we just do uh, basic this is node 1, right? Edge 0, node 2, edge 1, right? So graph dot node 1 dot append and node 2. And since this is an undirected graph, we're gonna create two entries here, node 1, right? So at this moment we have the graph. So now all we need to do is just like to traverse, right? We find any of the we start from any of the graph here, basically, or we can just always start. Basically, we can pick any number from this end, right? Because it doesn't really matter as long as it's a valid tree. It doesn't really matter which is our starting point, right? It will no matter what it will traverse. It can go through all the nodes, right? Uh, let's do a let's do a DFS traverse, right? So with DFS traverse, there are like two ways, right? There's like the recursive way and there's like a iterative way, right? Let's do a recursive. Recursive, I think, is the most intuitive way of doing it, right? So let's create a DFS here. DFS node, right? So it's very standard here. So and basically let's do and then don't forget. So since this is like an undirected graph, we also need to create like a, a global variable to because we don't want to stuck in this infinite loop, right? So we have to record which node we had visited before, right? So and then in the end we just do a DFS, right? DFS, let's do a start 0, right? And then we just add 0, right? Do a 0 to this visited, and then we do a DFS 0. So here, what do? We just simply do a for loop, right? For neighbors, right? Neighbors in the graph, right? So we find all the neighbors of the current node, and then we do another df and if, right? So basically we check if the neighbor is not has not been visited, right? Not in visited, right? Then we do another a DFS, right? So before doing the DFS, we just add this like node to the visited, right? uh, right. So in the end, once we done, we just check if we have visited all the all the nodes, right? Return uh, length of visited equals to n, right? Okay, but if we simply checking this one here, it's a so basically remember there's like we have two conditions, right? So the first one is this one. The first one is the if this tree if this this tree if this like kind of DFS traverse can visit all the nodes, right? In this case, we check if we have visited all nodes, but remember there's a second condition. There cannot be have any it can be any cycles or circles in this loop, right? So how do we check if this like this graph has a circle, right? We can simply, let's do a example. Let's assume that there's like 0, 1, 0, 1, 2, 0, 1, 2, and 3, right? And 4. What am I thinking here? And 3 here. So take a close look at this. So if it's a valid tree, then the edge number has to be equal to the number of the basic. Let's the number of nodes is 4 here. So the edge is always like the number of nodes minus 1, right? So let's say if there's a like if there's another edge here, right? And then we know any if there's a tree that has like the edges of this graph is more than the nodes minus one, then we know there has to be a graph a circle in this tree. So we can just simply before doing anything, we can just simply do a check here, right? If n if length, right? If length like of edges, right, does not equal to the n minus one, right? If they're not same, we can simply return false. So this will like basically this will cover two cases, right? And if this visit has everything, but this one is, but there's a circle, and then we know it will fail here, right? And if there's like two components, let's say 0, 1, and 2, right? And there's a 3 and a 4, right? So in this case, right? In this case, there's no circle, but they're not one. There's not there's it's a forest. It's not a tree, right? In this case, the edges satisfy this condition here, so it will go through this like for the DFS here, right? And let's assume we start from 0, right? We start from 0, and then once we finish once we finish this like DFS loop of 0, the visited will only have 0 and 2, right? Because it will not be able to traverse to the other subtree. So basically this will be false. Yeah, basically that's how we do the check, and it should work. Yeah, true. Cool. So this one works, and I'm going to talk about the iterative way of the DFS, since the the recursion is more is intuitive, but it's kind of sometimes it's kind of like inferior than the iterative, because than the iterative way, because DFS will have like this space storage overhead, right? Because every time it will need to store cache or store this like functions into the memory. So sometimes you also you it's better to use iterative way of doing the DFS. How, right? Same, right? I'm gonna so the same thing. So instead of doing here, doing a DFS here, right? So we also need to do a visited, right? And then for the DFS, it's a stack basically, right? So we're gonna use a stack. Stack is to be a put 0 in there, right? Basically while stack, right? While stack, and then every time we pop, right? We pop the current node, right? Stack dot pop, right? And then same logic for this DFS, right? For the current node, we do a neighbor, right? In graph dot node, right? And if neighbor, same check. Basically, that we can just basically copy and paste that the above code, not in visited, right? And then we just first add this visited, right, to this neighbor, right? Uh, with this neighbor, and then we just simply like append, right? Append this neighbor to the stack, right? Stack dot append, and append neighbor, right? Yeah, because we are doing this like a stack here, so right, so we append this one, we append the neighbor this 0 here, and then the neighbor 1, and then the neighbor 2, right? But once we finish looping the neighbors, we'll pop this thing out first, right? Basically, we'll start from here, and then we'll add this one's neighbor here. That's how we do it, because we always pop from the top. That's what makes this for loop a while for loop, like a DFS, because we're not if it's I mean if we're popping from the left, then this is going to be a breadth first search. Uh, okay, so then we can just simply remove that, right? We just remove this one here. While stack, yeah, I think that's the only difference is, yeah, the other one, the recursive way we use a helper functions, and this one we just use a stack, and that should do it. Yeah, cool, right? And then, like I said, another way is to do a BFS. So it's similar, it's just it's your own preference. You don't have to use any. You can choose any of your favorite preferred way of doing it. So like I said, if you're doing a breadth first search, in this case, it doesn't really matter, right? So we do a we need to use a queue here basically, right? So and then gonna be collections dot dequeue, right? And then same, we're gonna add this zero to the dequeue method here. So and here every time, right, we do a pop left, queue pop left basically, right? That's how we do a breadth first search. We always start from the left, right? And then uh, yeah, and then here same, right? So it's gonna be the queue, but we instead of but same thing. But we still append on the right side. But when we pop from the left, right? And then that's it. Okay, cool. Yeah, so that's the like basic like BFF, DFS, and then there's this union find, right? Okay, so so how does this union find can help us find the if this like if a graph I'm sorry if this like edges can form a tree or not, right? Like I said, and for the union find, right? It's the same thing, right? So we have a find, right? We have a find method, and then we have a union, right? So with union find, uh, we still need this check here first, right? That's always going to be our check. But and how this union find will help us detect a circle, right? Basically, we'll be using a union find uh, to detect a circle. That's the use of the union find method here, right? So how we are we detecting a circle? Let's say there's a like 0, right? And 1, 2, uh, 3. And okay, let's give it a 4 here. Let's make it circle a little bit bigger. And then there's a like a circle. So here is a circle, right? So how does union find do, right? So if you guys remember, so the find, right? The find method for each of the x, right? And union is the x and y. So find will give you all the will give you the root node of this of the subtree, right? And the union will basically union this x and y based on the rank of the root of x and the root of y, right? So while so basically we'll be looping through all the edges. For all the edges, we'll be try to union those two nodes, right? So while we're unioning those two, remember, so with the union find at the beginning, we're gonna have a parent node. We're gonna have a parent arrays here, right? At the beginning, each node, each nodes are the parents or parents or roots node is itself, right? So basically, we're gonna have like parents node from 0 until to n minus 1, right? At the beginning, each node, the parent node is the same as itself. And while we're doing the union, right? So let's say how union can help us detect a circle. Let's say we union 0 and 1 first, right? We have 0 and we have 1, right? And then 0, 1, they before union, right? So basically, every time we do a union, we find x and y. We find x the root 1, right? Root 1 of the x, right? We do this one. And the root 2, right? It's going to be the the root of the y here, right? So every time we do a union, we do this, which will get these two roots. Ideally, before union, this root one and root two, they shouldn't be the same, right? Because let's say because at the beginning, each one there each one the root is different. But since while we're doing the union here, right? So let's say we do a 0 and 1. After we do a union, the find of 1 will become 0, right? And let's do we keep doing it. We union 0 and 1, and then we union 1 and 2, right? And then after doing this, 2 find of 2 will also be 0, right? Same thing. Let's keep going. And let's union 2 and 3, 3 and 4, right? So at this moment, right? Once we have union all the edges until 4 here, so all the 0, 1, 2, 3, 4, all of their find, let's find 0, 1, 2, 3, 4 will both become, they're all 0, right? But then let's try to union this edge, right? It's going to be 1, 4, right? So find 1 and find 4, right? So you will get two zeros here, right? So every time, so basically as long as we see two roots have the same, sorry, have the same value, then we know there has to be a circle, right? Yeah, basically that's how we use union find to detect the circle. Okay, so let's do a union find here. Uh, since we're doing this like if check here, I'm gonna leave that at the top there, right? So we always use that. We always need that to make sure that the edges satisfy the minimum requirement of a tree, right? So with this check, we can save a lot of logic down the road here. Okay, let's do a find, right? So let's define a find and union. I'm not going to use those like very concise way of coding it. I'm gonna just write the very uh, classic like union find template that can help you guys understand. So I'm gonna use this like version of a path compression, right? I think I I briefly explained what is a path compression in the other videos. I'll try to explain it later. So basically, if there's a yeah, so first we have to have a parents, right? Parents like the at the beginning, each of the parents it's the node itself, right? And then there's going to be a ranks, right? At the beginning, each rank, all the ranks is 0. So if parents, right? If parents dot x is not to x, right? So basically means we do a recursive call. Meanwhile, we also do a path compression, right? And find, right? And then in the end, we just return parents, right? So okay, I'll explain this one more time here. So basically, if the parents does not equals to x, right? Then we know we need to keep going. Why? Because uh, 0, 1, and 2, right? Why? Because for 0, remember when we initialize the parents, right? The 0 of parents it itself, right? But one's parent is 0, two's parent is 1. So while we're traversing 2 going up until we reach the 0, this condition will always be false because once we're 0 here, the parents of x is 0 and x is also 0, right? Because that's when we stop. So what's the path compression, right? So from if we find 2, no, let's say there's a 3 here. Let's say if we trying to find 3 here, or let's try to find 2 here. And so every time, right, you need to go all the way up to the node, then you can find it. But then that will be gonna be a O n time, right, to do a find here. So, but we can flatten the tree because we know. So every time, right, when we first do the find the first time, so we'll while we're traversing back to the top, we'll also be moving all the nodes, right? The two the node itself plus all its parent nodes to enter the root node, right? That's how we do the flatten. Like so, after this one, it's gonna be 1 and 2 and 3, right? And then the next, so in this case, the next time when you do another find, you don't need to traverse back. You can just simply return this like root within O1 time. So basically, the first find of any element of any node will always be ON, but the second time and then but starting from second time, the time will be ON. So this seems like this is like uh amortized time complexity. So it's gonna be like O1, right? Cool. And okay, so uh let's finishing this one, union, right? The union is gonna be X and Y, right? So like we said, so to union X and Y, first we need to find the root of those two, right? And then if R1 is not equals to R2, right? Then we do a union, right? Let's finish the union method here. So and we'll be using a ranks, right? So the ranks will just help us to to more to to improve the time complexity even more, right? So because we always want to find a smaller rank, and then when we have those two roots, right? We have to decide we either merge R2 to R1 or R1 to R2, right? But how? So we're gonna use a uh, ranking system here. So we always rank the merge the the root with the lower rank to the higher rank. So in that case, it can help us like reduce the find overhead in the future. Okay. So we basically check ranks, right? If ranks R1, right, is greater than ranks R2, right? In this case, uh, R R2 has a lower rank, so we just merge sorry R2, right, to R1 with R1, right? Else if ranks R1 is smaller than ranks R2, right? In this case, same thing. We're gonna merge R1 to R2, yeah. And else if they're the same, right? If they're the same, it doesn't really matter. We can just randomly pick anyone to merge to another one. In this case, let's merge R2 to R1, right? So after this one, I'm gonna increase the. I think in this case, every time when we find the same ranks, we just simply increase the rank by one. Yeah, or there's some other ways, right? For example, if you can every time when you do the rank, you just let's assume there's like a set, right? You can use the size of the set of these two subroot to determine which rank is lower and higher. But in this case, all we have is a number, right? We have the number, and yeah, we don't have a array or list as a concept. So basically, that's how we basically every time we see a different the same ranks because at the beginning it's 0, we just always we just always do uh, a ranks plot just plus this rank R1 increased by 1. We're just simply using this one to simulate these ranking systems, right? And remember, right? So since we're using the union to detect a circle, right? Like I said, if it's not the same, then we just do a normal like union. But else, right? What does else means? Else means they're the same, right? Then we know there's like a circle, right? So let's just use this union here. I'm simply just returning true and false here to so basically return false means okay the union failed, right? Why it failed? Because we see a circle. Circle means we didn't do the union because they are the same. There's no way, there's no need to union them again, right? Since they're already union. But if they're not, then we just return true here. Rn, right? So we just simply, in the end, we just simply like loop the edges, right? And we just do a union, right? If, right? If not union, basically, if not union, edge 0, right? And edge 1, right? So edge 1, right? If it's not union, basically, if it's a false, and then we know if there is a circle, we just return false, right? Basically, because we're checking if it's a valid tree or not, right? So if there's a circle and then we know it's not valid, we return false. If everything works fine here, right, and then we return true here. Yeah. Uh. Oh, sorry. Yeah, I missed this colon here. P oh, sorry. Yeah, parent. All right. Cool. See, okay, it works. All right. And yeah, so basically that's the that's all I can think of about this problem here. DFS, BFS, and the last one, the union find. Uh, cool. I hope you guys enjoyed this video. Thank you so much for watching the video. All right. I'll see you guys soon. Thank you. Bye bye.